we should move ahead. And our next talk will be presented by Evgueni Goudzovski, NA62 at CERN, recent results and prospects. Evgueni, hear us?
Yeah, I can hear you.
Yeah, please share your screen.
So I'm going to be presenting the recent results and prospects from the NA62 experiment at CERN. Thanks a lot for the invitation. Well, unfortunately, this is not going to be a fully dark sector talk because the main results from NA62 come from studies of chaos decays, rare chaos decays, but there are quite a few new results from searches for the hidden sector in chaos decays that I'm going to present here, along with the Pioneer bar result. So just to remind you that the main reason for the existence of the NA62 experiment are the two very rare kaon decay modes. In particular, the golden modes in kaon physics are the decays of a kaon into a pion and a neutrinity in a pair, which proceed in the standard model by the Z-penguin and box diagrams presented here. And this makes them very rare decays. And additionally, the standard model predictions for these decays are very precise at the 10% level. And therefore, they are of prime interest for kaon physics. They're characterized by maximum CKM suppression, no long-distance contributions from amplitudes with intermediate photons, and importantly, the hadronic matrix element is extracted from the measured rates of dominant semi-leptonic kaon decays by isospin rotation. So the table here summarizes the standard model predictions for the decay rates of the K plus and K long into Pioneer bar, and you can see that they're just below 10 to minus 10. And one thing that I'm going to present today is the final NA62 result on the measurement of the K plus to Pioneer bar decay rate based on the full run one data set. Well, just to tell you a few more words why the K to Pioneer bar decays are of such an interest. So first of all, their theoretical standard model rates have a 10% uncertainty. But very interestingly, various BSM contributions give rise to large modifications of the decay rate, up to a factor of 2 or 3. And most importantly, there are strong correlations between the BSM effects on the K plus and K long branching fractions, which are summarized in this two-dimensional plot here of the branching fraction of K long going to Pioneer bar versus the branching fraction of K plus going to Pioneer bar. One can see here the standard model expectation with a 10% precision, and then different new physics models might lead to different modifications of the two branching fractions, importantly with different correlations. Therefore, one needs to measure to a precision that matches the standard model precision, both the branching fraction of the K plus decay mode and the branching fraction of the K long decay mode to understand which kind of new physics is at play in case any of these branching fractions are different from the standard model predictions. This brings me to the NA62 experiment at CERN, which is part of the broader experimental program. CERN has been hosting kaon experiments for many decades, actually, and just in the last 20 years, there have been 5 different kaon experiments, starting from the NA48, which is famous for the discovery of direct CP violation in the case of neutral kaons to pions, which was followed by NA48-1 and NA48-2, the lepton flavor universality phase of NA62, and finally the NA62 itself, which collected its first data during the run 1 in 2016 to 2018, with the main goal being the measurement to 10% precision of the K plus to pi plus Pioneer bar decay rate. And geographically speaking, all these experiments, all these kaon experiments, including the NA62, are located in the ECN3 hole in the north area of CERN. And they're using a 400 GeV beam extracted from the SPS accelerator to produce a secondary kaon beam. So this is the sketch of the beamline and detector. So the 400 GeV SPS protons nominally at an intensity of 3 times 10 to 12 protons per spill of about 3-second duration, are used to produce a secondary count beam with a mean momentum of 75 GeV over C and a short and narrow momentum band. We call it the count beam. However, it's actually mainly a pion beam, with the count component being only about 6%. So the nominal beam rate is 0.7 gigahertz, of which the count rate is about 50 megahertz. And there is a large, about 80 meters long vacuum tank housing the fiducial decay region. And the rate of count decays in the fiducial volume is about 5 megahertz. So about 10% of all the counts coming into the vacuum tank actually decay in front of the first spectrometer chamber. The experiment is equipped with 2 trackers. There is an upstream tracker for the beam particles and a downstream tracker consisting of 4 straw chambers, large straw chambers placed in vacuum for the products of count decays downstream. Importantly, the downstream tracker operates directly in vacuum to minimize multiple scattering, and this is a high vacuum of the order of 10 to minus 6 millibar. Then there are the 2 Cherenkov detectors, one for the incoming counts to identify positively the incoming counts, and the other one for the products of count decays, and they collectively provide a time resolution better than 100 picoseconds. And the detector is also equipped with a colorimetric system, with a muon detector, and uniquely with a hermetic photon veto system, which means that the chance of a photon produced in the vacuum tank to escape is very small. Indeed, for the pi 0 to gamma-gamma decays, a suppression factor of about 10 to minus 8 is achieved within the pi-nu bar analysis. So, as I mentioned already, the experiment has collected its run 1 dataset in 3 years, 16, 17, and 18, in totally collecting about 2 times 10 to 18 protons on target in count mode, which leads to about 6 times 10 to 12 useful K plus decays in the vacuum tank. And it's interesting to mention that also in about 50 hours, a few times 10 to 16 POTs have been collected in dump mode. Indeed, it's very easy for the NA62 experiment to switch between the count mode and the beam dump mode. And this test sample is being used to validate the possible searches for new physics in beam dump mode. And the run 2 of the experiment is starting in about a month from now, and it's going to proceed at a higher intensity than the run 1 of about 3 times 10 to 12 protons per pulse. So let me briefly describe the measurement of the pi-nu bar decay based on the 3 papers listed here. So the 2016 and 17 data sets were analyzed separately, and this is followed by the analysis of the full data set in a paper which is accepted for publication in JHEP. Well, just to give you a brief reminder of the charge count decay physics and the main principles, and to explain the main principles of how the pi-nu bar decay could be searched for. The first of all, one could plot the decays of the charge count in this 2-dimensional plane with the momentum of the outgoing pion on the x-axis and the square of the missing mass, which is the difference of the count and pion full momentum square, on the y-axis. So we can see here, well, the most relevant features of count decay physics. First of all, there are the 2 bands, one corresponding to the pi plus pi 0 decay, that's a 2-body decay, and the other one corresponding to the K to mu decay. And finally, at very large missing masses, you can see the excess of events due to the 3 pion decays. So the first principle of a K to pi bar search would be to define region 1 and region 2 in such a way, kinematically in this plane, that the main count decays are outside of these regions. So there is a factor of the order of 10 to 3 kinematic suppression of the main decays, and indeed they enter the signal region only via the tails. And on top of this, there is a 10 and 8 orders of magnitude colorimetric suppression. to discriminate pions against muons. And for the K to pi plus pi 0 decay, there is an 8 orders of magnitude suppression of the pi 0 in the final state due to the hermetic photon veto system. This is how one could reach a signal to background ratio much better than 1 for a branching fraction, which is below 10 to minus 10. Well, just to give you a few key parameters, it's very important to keep the timing extremely precise at NA62. So as I mentioned, the timing is below the 100 picosecond level, which is crucial in order to reduce the effects of accidental activity to an acceptable level. But interestingly, if we look at the dependence of the timing difference between various detectors and the dependence on the resolution of this difference between various detectors, then indeed they are stable over very long periods of time, over the whole several years of running, to a precision of a few picoseconds. And that's a very important property of an NA62. So this brings me to the single event sensitivity, which is defined as the branching fraction of the pi bar decay, which corresponds to the observation of expected one signal event. And in terms of signal event sensitivity, the run one data has achieved a value of 10 to minus 11, which is exactly 10 times smaller than the standard model branching fraction of pi bar. So indeed, we expect about 10 signal candidates in the whole run one data set. Well, and I'm showing two plots here just to illustrate the most important features relevant for pi bar measurement. First of all, to measure pi bar, one has to veto any activity downstream to make sure this is not one of the background decays. The pi bar is essentially decay of with one track coming in, one track going out, and nothing in the final state. And therefore, by doing so, one introduces an effect called the random veto, which is the probability of vetoing or rejecting a signal event because there is accidentally some activity in time in one of the downstream detectors due to an accidental event which is not related to the pi bar event. And that's one more reason why the timing resolution should be good. And one could see that this random veto efficiency scales more or less linearly as a function of beam intensity, of the instantaneous beam rate. And indeed, there is a 1/3 loss of signal events due to the random veto. So this is one of the major challenges for this kind of ray decay measurements. Well, not just for pi bar, but also in general. And on the right-hand side, I'm just showing the plot of the trigger efficiency for the pi bar channel as a function of instantaneous beam intensity. And the trigger efficiency is about 90%. This is a dedicated trigger built specifically for pi bar measurements to be selective. So just a few words on the analysis strategy. So after the background evaluation, well, there are the two signal regions, region 1 and region 2, in display of the pi momentum and missing mass square, which are kept blinded all the way. But importantly, there are also 5 control regions which allow the validation of the background predictions in the K3 pi channel, in the K2 mu channel, and pi plus pi 0 channel. And after the background is estimated, the control regions are opened first to validate the background expectations with the data, and only later we proceed to the opening of the signal regions. Well, I think I'm going to skip the details of how exactly the backgrounds are evaluated. I just wanted to mention that, well, the backgrounds due to pi plus pi 0 and K-2 decays, but also K3 pi, enter due to the kinematical tails, the non-Gaussian kinematical tails of reconstruction. And here I'm showing the missing mass specs from the pi plus pi 0 decay. One can see very long kinematical tails spanning into the signal region. Importantly, these tails are measured directly from control samples. So for the main background sources, the background estimate is fully data-driven we do simulate these tails, and this plot actually shows a very good agreement between data and simulations in terms of description of the non-Gaussian tails of the two-body signals. However, the backgrounds are always evaluated using the controlled data sets directly. And one interesting point that we discovered while working on the background evaluation is that actually the main backgrounds don't come from the count decays in flight in the fiducial decay region, contrary to our expectations. They actually come from the upstream sources. Well, this plot just gives you, this sketch just gives you one example of a background coming from an upstream source. One could imagine a count decaying well before it enters the vacuum tank, for example, into pi plus pi 0, then both photons from the pi 0 decay are lost. What we see in the vacuum tank is a pion from an upstream count decay, with its trajectory being affected by the magnetic field upstream. And there is an in-time pile-up beam pion, which provides the upstream track. And eventually, this might lead to a fake vertex with a pile-up beam particle, which looks like a signal event. And actually, we have discovered even something more interesting. When the counts decay extremely far upstream, and the pion from the count decay, well, has a certain trajectory in the magnetic fields, and actually it could overshoot the final collimator and eventually re-enter the decay region, leading to a fake vertex. So, in order to, well, the most important thing that we've been doing in terms of improving the pi bar measurement was the improvement of the original beamline, and to prevent the largest problem, which we have discovered, which is due to the pions overshooting the collimator, we have replaced the old collimator with a current collimator. So you can see on the left how the old collimator looked like. It's a fairly small device, while on the right-hand side, you can see our new collimator, and this has largely blocked an important source of upstream background, which also allowed actually improving the signal acceptance by about 60%, because one could relax the cuts on the signal acceptance. Well, and this is, okay, sorry for this busy table, but this is the final background table for the samples with the old collimator and the new collimator in 2018. Well, just to notice that the sample with the new collimator is about 4 times larger than the sample with the old collimator. So we replaced the collimator early on during the data taking. So one could see that there are certain backgrounds from count decays in vacuum tanks, and all of these are estimated with the data-driven technique. And there is the upstream background, which is also estimated with the data-driven technique. However, interestingly, in both samples, the upstream background, which is not even due to count decays in the vacuum tank, is still the largest background. And that sets the way towards the measurement in future. So we have improved the beamline layout, and we have installed several new upstream V2 detectors, and actually also one downstream V2 detector, to bring the pi nu bar measurement and other measurements in run 2 into a low background regime. So this is the pi nu bar box opened. One could see 17 events in regions 1 and 2 in the 2018 dataset, which leads to 20 events in total in the full run 1 dataset, while the expected background is about 7 events. And one could see these events here in the one-dimensional projection in terms of the missing mass. And this leads to the final result on the pi nu bar measurement based on run 1 sample. So that's 11 units plus minus 4 times 10 to minus 11, which is the first evidence for the pi nu bar decay, making it one of the rarest particle decay to be ever observed, with a branching fraction of the order of 10 to minus 10. And the significance of this measurement is 3.4 sigma. And well, this brings me to this historical perspective slide, which shows that finally NA62 managed to observe the K2 pi nu bar decay after 50 years of improving limits on this decay. Now let me move on to the multiple.
Evgeny, sorry, 5 minutes left.
Oh, really? Okay, well, I'll
Yeah,
try
yeah.
to be a bit quicker. Sorry, okay. Yeah, now let me move to the results on the hidden sector searches. I'm going to present results from 7 papers here, including searches for invisible dark scalars and searches for heavy neutral leptons, which were performed with the same data set. Well, first of all, let's look again at the pi bar measurement. And the pi bar measurement could be immediately interpreted as the search for an emission of an invisible X particle produced with a pion in the Kelvin case. So region 1 corresponds to X masses up to 110 MeV, while region 2 is between 150 and 260 MeV. And this could be interpreted as dark scalars, UCD axions, ALP, and so on and so forth. And that's very interesting. For this measurement, the main background is the K2 pi bar decay itself with a branching fraction of 10 to minus 10. And then by comparing data NMC in the region of pi plus pi 0, where we veto the pi zeros with a probability of, well, with a factor of better than 10 to the power of 8, we could also search for the decay of pi 0 to invisible, and observation of this decay would be clearly BSM physics, and this is reinterpreted as the search for a K decay to pi x, with x being in the vicinity of the pi 0 mass between the pi bar regions 1 and 2. So these are the results of the search for K going to pi x in regions 1 and 2 by interpretation of the K to pi bar analysis. So the results are presented as a function of the assumed X mass and as a function of the assumed lifetime. The results are the limits on the branching fractions are the strongest, down to 10 to minus 11 for very long lifetimes, in excess of 100 nanoseconds, let's say of 10 nanoseconds. This is because the analysis is mostly sensitive to invisible X, and the limits weaken as we go towards shorter lifetimes, assuming that the decays are into standard model particles. So on the right-hand side is the interpretation of this result in terms of the physics beyond colliders model BC4, which is a dark scalar model with a dark scalar decay into visible standard model particles only. And one could see that we have achieved 10 to minus 8 in terms of the sine square of the mixing angle, and we improve substantially on the previous Brookhaven results. Now let me talk briefly about the search for pi 0 going to invisible. Here the key point is the rejection of the K going to pi plus pi 0 decays, with pi 0 going to 2 photons. I already mentioned that for the K to pi bar analysis, we achieved a 10 to minus 8 rejection of pi 0 going to gamma gamma. Actually, we have tuned the selection, and in particular the pion momentum range cut for the pi 0 to invisible analysis to achieve a rejection of 3 units 10 to minus 9 for this particular analysis to reduce the background. And we have analyzed about a third of the 2017 data set. And we expect about 10 events, and we observe about 12 events in the pi plus pi 0 region, which leads to an upper limit of 4 units 10 to minus 9 for the branching fraction of pi 0 to invisible. And going one slide back, this purple curve here corresponds to the exclusion limit on K going to pi x in the vicinity of the pi 0 mass in terms of this particular model. Finally, let me spend a few minutes to discuss the searches for production of heavy neutral leptons at NA62. So well, first of all, we search for a heavy neutral lepton produced in Kelvin decays with a positron, and luckily we can exploit the pi bar trigger chain, so it's not downscaled. While for searches with a muon, we exploit the control trigger chain, downscaled by a factor of 400, which leads to about 10 to 12 counts in the fiducial count decays in the fiducial volume for the positron case, and about 10 to 9 in the muon case. So here I'm presenting the plots of the squared missing mass for the positron and muon case. One could see a 3 millions of the standard model KHU candidates with a branching fraction of 10 to minus 5, and the signal would be a spike on the right-hand side on top of the continuous background. Unfortunately, there is a very large irreducible background from K-mu2 decays with muon decays in flight, and it's suppressed by good vertex resolution, but it's irreducible. Well, in the muon case, we actually observe 2 billion standard model candidates, and the main backgrounds to HNL production come from radiative decays, K to mu gamma, and the K-mu3 decays. And by searching for spikes here and using data-driven background estimates, we arrive to this kind of limits on the HNL mixing UL4 square versus the mass. So the curve at around 10 to minus 9 here is our exclusion for the positron mode, right? And it goes from 140 MeV to about 460 MeV. And the dark blue curve here is our exclusion for the muon mode. So we have reached the sensitivity of the Brookhaven experiment, and we have extended the search range to about 380 MeV. And well, you can also see that we exclude part of the BBN allowed range. Well, I'm using here the curve for the BBN allowed range dating back to this paper of the year 2000. And we also put a limit on the branching fraction of K going to mu and 3 neutrinos of the order of 10 to minus 6, and a similar limits on the branching fraction of K plus going to mu nu and X. So I think I will skip the future plans. I will just mention a few things. So first of all, the goal of run 2 is to run at high beam intensity with an optimized beamline and UV detectors and an improved beam tracker in order to squeeze the precision on the pi nu bar measurement, K plus going to pi nu bar, from the current 30% to about 10% to match the standard model prediction. And in addition, it's approved to collect 10 to 18 protons on target in beam dump mode in up to 90 days of running. So these are the plans for 21 to 24 for the run, which is starting next month. And I think at this point, I'm going to skip to the summary. So we have collected 6 times 10 to 12 count decays in flight in run 1 in 3 years, corresponding to 2 times 10 to 18 POTs, which has led to the first evidence for the K plus to pi nu bar decay. And we're using this sample, which has multiple trigger lines to search for hidden sector mediated production and other BSM physics, including searches for invisible scalars produced with a pion and searches for HNLs produced with a lepton, and some other searches are in progress, and we will produce more results shortly. And we are starting we are preparing to the start of run 2, which will lead to an even larger sample collected with a better detector and a better trigger, and something I didn't touch upon, but in the long term, there are other plans for the high intensity count beam facility at CERN, which will further improve the precision of K to pi nu bar and will include a K-long experiment. So even larger decay samples will be collected. Thank you very much. I hope I didn't exceed my quota too much. Thank you.
Yeah, thank you very much, Evgeny. Questions, please.
May I ask one?
Yeah, please.
Evgeny, well, which physics do you plan to study with 19 days of beam dump mode?
Well, I think it's physics, which was very nicely presented by Guy at the beginning of the meeting. First of all, searches for decays of heavy neutral leptons produced in the dump, searches for axion-like particles, searches for decays of scalar particles in general, and dark photons. So, well, that's a standard, I would say, standard beam dump physics, which is not very different from, let's say, the chip physics case, except that our sensitivity is not.
Yeah, but do you have any plots with sensitivities for this 90 days? I mean, you somehow limit the amount of protons, like 10 to 18. It should be motivated by some I don't know, some particular model or whatever.
Yeah, well, actually, with 10 to 18 protons on target,
Yes.
we are going to be sensitive to, well, we're going to be improving on the present limits for both heavy neutral leptons and dark scalars and dark vectors. Well, I think.
But do you have any plots with
Well, I
your?
don't have in this talk, but
You can find in my presentation, Dima.
Exactly for this 19 days. Yes, I mean for
Yes,
this.
yes.
for
In
this
my
statistic.
presentation, you have 10 to the 18 POT, which is what NA62 released as official projections.
Okay, thank you.
Right, thank you.
yeah, sorry.
Okay.
Well, I skipped them because that's a talk on behalf of an NA62, and I knew that Gaia was given an introduction anyway. Yeah, it's exactly the same projection. Yeah.
Okay. Okay. Any other question? If not, thank you very much, Evgeny, again for very interesting talk.